Great. Okay, so the first talk is by Diana Morosan from the University of Helsinki, and Diana is an expert in LOFAR radio imaging spectroscopy and solar radio bursts. And for the first hour, she's going to give an introduction to solar radio bursts. So as I say, Diana, it is an hour. You may get some questions during, and then a few after as well.
Okay, thank you. Hello, everyone, and thanks for having me here today to give a very brief introduction to solar radio bursts. There's only so much that can be covered about radio bursts in 1 hour, but I'll try to do my best and cover most of the radio bursts you might see with LOFAR at some point if you look at solar radio data. And I have a quick outline of what I'm going to talk about today. First of all, I'll outline some of the radio emission from the sun over wide frequency range. Then we were going to look at the traditional low frequency radio burst classification. And this is made of 5 main types of radio bursts, 1 to 5, which I'll talk about each of these types a little bit next. And finally, there are a few radio bursts, well, quite a few radio bursts that don't fit into this classification. And I'll outline some of these and give some examples, and then a short summary at the end. And well, first of all, is why would we bother to observe radio waves at all? Well, if we look at the electromagnetic spectrum that actually reaches the ground, we realize that's actually quite limited. So because of our atmosphere and ionosphere, a lot of the radiation gets absorbed, and the amount of electromagnetic radiation that comes in is actually limited. So there's one small window in the visible range, a little bit in infrared, but then if we go at higher and higher wavelengths, there's quite a big window in radio. So a lot of emission at radio wavelengths from gigahertz to like 10 megahertz comes down here on Earth, and it's easily observable from the ground. And this is very important because ground space observatories can be made relatively cheap. They're a lot cheaper than a big space mission, for example, that needs to observe in ultraviolet or infrared or X-rays. All of those needs to go up into space to observe, and they cost a lot of money, while radio waves can be observed directly from the ground, and they can be observed with a relatively cheap instrument. Now, I know LOFAR is not very cheap, the International LOFAR Telescope, but compared to a space mission, it is quite a lot cheaper. So it is very important to make use of this radio window that we can observe from the ground. Now, unfortunately, not all the radio waves arrive. A lot of them get stopped by the ionosphere around 10 megahertz. So anything below 10 megahertz also has to be observed from space. Okay, so let's go back to solar observations. And I think you've had some lectures yesterday on solar activity, flares and CMEs and so on. And I hope we all know what the sun looks like at visible wavelengths. Just have to move this. So it's very uniform, occasionally has few sunspots. And this shows the solar surface or the photosphere. But if we switch wavelengths to extreme ultraviolet, for example, what we see is the solar corona. And occasionally we see these bright active regions on top of the sunspots, which are the regions where most solar activity originates. To radio. So this is a LOFAR image at radio wavelengths around 135 megahertz. And compared to this, and even a visible image, the radio image does not look like much. It's basically a fuzzy blob in the sky, and most of the emission mechanism that contributes to what we see is Bremsstrahlung emission. And Owen will probably talk about this in a little bit. But you're probably wondering why bother observe radio at all, since all we see is this. Now, occasionally in radio, we see bright blobs or bright spots like this, and usually associated with active regions. And it's these bright patches refer to areas where particles are accelerated, and the accelerated particles cause instabilities and wave-particle interaction and give rise to radio emission. And the difference between radio and ultraviolet, where we can see a lot of detail, is that radio can tell us where we get particle acceleration on the sun, in ultraviolet, we only see hot loops, for example, but we wouldn't get any ideas of particle acceleration. And another reason why bother observe radio on the sun at all is, oh, there we go, is this plot here. And this explains very well the importance of radio emission, and Owen's gonna explain in a lot of detail all these different radio emission mechanisms on the sun. But what I want you to gather from this plot is that if here we have frequency from low to high, kilohertz to gigahertz, this is height above the photosphere. If you look at these lines here, there's almost a linear relationship between frequency and increasing height. So the emission mechanism and the height of the emission gives you an understanding of where in the solar corona various processes happen. So at tens of gigahertz or higher, its gyrosynchrotron emission is dominant. Again, Owen will explain it in a lot of details. It's just electrons spiraling along magnetic field lines. Then Bremsstrahlung emission is dominant, but then as we go lower and lower in frequency, we get to a place where plasma emission becomes dominant. And this is very important because plasma emission can show you where accelerated electron beams originate. And this region here, this is where low frequency radio bursts also dominate the radio spectrum when there is solar activity. And this is also what you could observe with LOFAR and other low frequency radio telescopes. So this brings me to solar radio bursts. And I want to make a distinction that there are radio bursts across this entire radio window. There are radio bursts at microwaves and so on, but what I'll be talking about today is specifically low frequency radio bursts at a few tens to a few hundreds of megahertz. There's a lot of other different radio bursts there, but the emission mechanism of those radio bursts that occur in that range is mainly gyrosynchrotron, and I will not be talking about that much. Sorry? Okay. And I will not be talking about these. Okay. I won't be covering much of these today, but this frequency range here that looks at low frequency solar radio burst. Okay. Now, if we think about solar activity and we have a flare, which is a sudden release of electromagnetic radiation. So all of a sudden we get, if we go to start this movie, we get a sudden brightening, and also material can be expelled outwards that will form the CME. So the sudden brightening is our flare. And then in this movie, we can also see a CME just blowing away from the sun. What usually happens if we look at radio emission is that once we get that sudden release of electromagnetic radiation, that's also that can also be accompanied, not all the time, but it can also be accompanied by fast electron beams. And those fast electron beams, the first radio signature that they produce are a radio burst called type 3 bursts. I'll stop there just to explain this here. This is how we look at solar radio bursts. So we look at many, many frequency channels over time. And we call this a dynamic spectrum. And every now and then we see different shapes, different bright shapes that are classified into different types of radio bursts. So the first thing we see when a flare happens, well, we can see, because it's not always the case, we see these very almost vertical lines in dynamic spectra, and those are called type 2 radio bursts. And they're just electrons escaping along the field lines. There's also, I will mention this a little bit later, it's not very well studied, but there's some diffuse emission like fuzzy emission following type 2 radio bursts, which is called type 5. But that is quite rare, and I think it's a little bit forgotten at the moment. Now, we have our flare release of electromagnetic radiation, but then the CME can erupt. And accompanying these CME are these sloped lines, and they look something like this in dynamic spectra, and they're called type 2 radio bursts. And also, most likely accompanying the CME and the flare, we can get fuzzy emission covering a wide band, a wide frequency band. And that's called the type 4 radio burst. Here it's labeled as flare continuum. And this broad emission covering a wide band can also occur in the absence of flares and CMEs when it just accompanies these active regions here. And it's a type 1 noise storm. And I'll show you an example of this now. Oh yes, and the reason we usually invert our frequency axis because since the plasma emission is dominant emission mechanism and the plasma frequency is proportional to the square root of electron density, as we move further away from the sun, the frequency also decreases. So this is a measure of, you can think of it as a measure of height away from the solar surface. So solar surface here, the radio burst will travel to lower and lower frequencies. And I'll show you this shortly, how it works in terms of type 3 radio burst.
Diana, can I ask a question about the,
yeah.
You mentioned about the type 5 and you said it's not really well observed anymore, or no one mentions it anymore. I mean, has it just been subsumed into the type 3 phenomenon overall, or does anyone ever get the type 5?
I actually struggled finding some recent references for type 5 bursts. So I think, I don't know, maybe previous instruments weren't able to resolve that structure and they mislabeled it, or we simply, I don't know, people looking at type 3 radio bursts haven't observed this continuum following them.
Yeah.
So it's very, very strange.
Yeah.
Yeah, I'll have an example later and show some of the characteristics of the emission. But even if anyone here knows of anyone who has spotted something resembling a type 5, it would be nice to know, because
sure.
Yeah, I struggled to find anything recent on it.
Okay, thanks.
Yeah, no worries. Okay, so yeah, so this frequency axis here is simply a measure of height above the surface. So the lower the frequency, the higher up in the solar atmosphere we are. Okay, and some examples, these are all LOFAR examples. We have our dynamic spectrum, so a lot of frequency channels over time. And this blue background is a quiet period. And every now and then we see these bursts of emission. And these are our type 3 radio bursts. So they're almost vertical lines of emission and dynamic spectra. Now, type 2 radio bursts, this is also a LOFAR example. They're more sloped lines, so these type 2 radio bursts are quite short, a few seconds, while type 2 radio bursts can last for a few minutes to almost an hour. And they're simply bands of emission like this. And they have like quite a lower slope than these type 3 radio bursts. Type 1 noise storm, well, it's either type 1 burst or type 1 noise storm, and it's usually called a noise storm because if you look here, there's emission over the entire band. Oh, that's the sun. Emission over the entire band, but it's composed of multiple little bursts. So there are multiple very, very noisy bursts. And when it covers a wide frequency range and it can last for hours or even days, it's a type 1 noise storm. And this is an example of a type 4 radio burst. I think there's a question. I can take it now or later.
Yes, hi.
Yeah.
Sorry, I was wondering if we can apply the same method of analysis that we use on type 2 radio burst, but on type 3 radio burst, if we stretch the x-axis to see the slope very clearly, or?
So if you stretch the x-axis on type 3 bursts?
Yes, yeah, to see the slope.
Yeah, I think he means, can you monitor the drift rate as you can with the type 2s?
Yeah.
Exactly.
So,
yes.
Yeah, usually what we do is we point and click along, we zoom in and point and click along either the leading edge or the spine or the middle. And that's how we get the drift rate. Same, we could get the slope from it. the same as type 2s, but this time scale would be a few seconds, while this time scale is a few minutes. So that's the only difference. But we can zoom in and work on it the whatever way we want.
And what about the type 1? Can you do the same?
Oh, sorry. For type 1, yeah, you can also zoom in. So with type 1s, because these radio bursts are really, really fine structured, I think they're a second, one radio burst is a second or less, or maybe a little bit more. You need to have really high resolution data. So with LOFAR, you can zoom in and see its structure if it's a high temporal and frequency resolution. So it depends on the observing mode. Sometimes when you zoom in, you just see pixels with older instruments, for example. But with LOFAR, you can really see the issue with type 1s. If you zoom in on that feature here, it doesn't really have a slope. Each individual burst doesn't have a slope, a well-defined slope. It's just a blob, almost like a diamond-shaped blob.
Mm-hmm.
But there are chains of type 1s. So like this is, for example, a chain of type 1 bursts, and that has a slope. But I don't think anyone really knows what this chain of emission means. It's just emission from different altitudes.
But these are related to eruptive events, right?
No,
not quiet time or any time they can show.
So type 1 noise storms, while type 2, type 3s, and type 4s, they often, especially type 2s and type 4s, they need to have either a flare or CME occurring. Type 1 noise storms, they just sit on top active regions. And even if the active regions don't erupt, so they don't have any significant flares, they sit on top of active regions and accompany them for days. So they're not necessarily related to they're actually not related to any eruptions, but possibly small processes in the active region. So I'll show a little bit later on it.
Can I ask one more question?
Yeah, go ahead.
Type 1s, so they sit above the active region, so presumably the variation, is it connected with the loop movement or something in the active?
Yeah, so it's unclear, but I'll show in a few slides. They're related to possibly the most recent studies suggest they're related to high coronal null points, where you have loops in such a way that can cause magnetic reconnection continuously.
Yeah, that was my question. Okay, thank you.
Thank you.
No worries. Okay, so yeah, type 4 bursts, they're just a bright blob over wide frequency range. Again, it's not as well structured as type 1s, but it can have structures inside. But I'll show more examples shortly. Yeah, and finally, putting it all together, if we have, this is similar to the cartoon I showed. If you have a flare, so in this case, there was a flare at CME in this observation here, and this is also a LOFAR observations. First thing we see are type 3 bursts, then we see the type 2 burst associated with the CME, and then a big type 4 burst over quite a wide frequency range here. And before the flare and CME, there was an ongoing type 1 noise storm. So this was not related to flare CME, but it happened before. So even long before this time, the type 1 noise storm was there all the time, just sitting there. So this is what you usually see in the case of an eruption. But it's not always the case. You can only have some type 3s, you can only have a type 2, you can only have a type 4, or some combination of these. And such an event is probably more typical of bigger eruptions, so larger flares or faster CMEs. Yeah.
Just wondering, have there been any studies of the occurrence of type 1s before type 3s or type 2s, or
so there's been
predictive power?
Yeah, there's been studies of type 1s before a CME, for example, because the CME kind of disturbs the loops around its eruption site. And in some cases, the type 1 disappeared after a CME, a type 4 appeared, and then the type 1 either completely disappeared or reappeared after the type 4. So there are a few studies. I'm not very familiar with them, but there has been a few studies on it. But as far as I know, there's no clear answer to what's happening even. Most of them are individual studies.
It would be interesting to see whether there's always a type 1 before, a big eruption or something like that. I don't know. Probably not, but
Well, it's possible, but it may be the medium may be modified by the eruption, so then the type 1 disappears. It really depends on the active region as well. Not all active regions have type 1s. Another question?
Yes, please. Does that mean that if we observe type 1 radioburst from some active region, is it referring to that maybe we can forecast or predict the launching of a CME or the likelihood of launching of CME from this region?
I don't think so, but I don't know. Maybe a type 1 could indicate a more complex high magnetic loops that would cause reconnection, but apart from that, I know there are big active regions that were accompanied by type 1s along their entire rotation around the sun, but those active regions only produce C-class flares, for example, or small M-class flares. So I honestly don't know if there could be any correlation between studying type 1s and trying to predict bigger eruptions, but they may predict more complicated magnetic fields.
Mm-hmm. Thank you.
Okay, and yeah, since we're talking about type 1s, let's move on to a little bit more details about type 1s. And the same example as before, they're just wide frequency band emissions. They can last for hours or days, or during the entire rotation of the active region across the disk. You can see the type 1 following it. And it's composed of these multiple fine structures that I mentioned before. And one interesting thing about type 1s is that they're highly circularly polarized. So if you look at total intensity light and then you look at the circularly polarized component, they almost have the same flux values or the same intensity level. So yeah, then because they're highly circularly polarized, they're probably fundamental plasma emissions, so occur at plasma frequency. If you image them, this is an example of, it's the same type 1 noise storm, but I think this one is a few days earlier, imaged with an Ansei radioheliograph. And if you look here, the high frequencies are at closer to the sun, lower frequencies further away, which we expect from the plasma emission mechanism because electron density decreases that way. And they just sit on this active region here. They just sit on top of this active region. And this type 1 noise storm actually followed this active region as it rotated across the disk that way. And this is what you'll see when you image a type 1. And regarding their origin, it's very, very much unclear. So they're observed on top active region. They can accompany them for days. And only recent studies have looked into a bit more detail. So for example, if you do coronal magnetic field extrapolations, like in this study here, they found this type 1 here to be associated with magnetic fields that are oriented in such a way that they produce really high coronal null points, because the type 1 is also quite high compared to other flaring processes. So you have and in this particular study here, they suggested that the closed loops from the active region can continuously reconnect with open field lines from neighboring regions. So these field lines are open and these are closed. They produce a null point and you get possibility of continuous magnetic reconnection there. And another study here, these little dots are the center of emission of the type 1 source, and also from high to low frequencies, and they're quite a bit higher up compared to the region is down here. But if we track it over time, it was found that there are loops oriented in such a way that they form also quite significant coronal null points. You can see some loops go in there and some loops go in there. And this also holds in extrapolations. There's a significant coronal null point there. So the most recent research suggests that they're somehow associated with either high coronal null point or magnetic processes that are capable of producing continuous reconnection events to have that emission on top of active region for so long. But it's as far as I know, there's more studies could be done. It's not clear what exactly causes them. Okay, Now, next up are type 2 radio bursts. And as I explained before, they're bands of emission. So you see bands of emission over, this case, they're over like 15 minutes or 20 minutes or longer. They can last also up to an hour or more if they're in interplanetary space. And they usually occur at the fundamental and the harmonic of the plasma frequency. So fundamental at 20 megahertz will have a harmonic at 40 megahertz here. So you have a fundamental band and the harmonic band in dynamic spectra. And sometimes these bands are further split into something called split bands. So the harmonic has split bands, 2 bands, and the fundamental also has 2 bands. But the interesting thing about type 2s is that if you were to zoom in on any region, they're not just smooth bands, like, for example, the type 3 bursts. Sometimes they're just a smooth burst traveling upwards. They're composed of numerous fine structures. So there's numerous complicated processes that produce electron beams in such a way that you get all these funny shapes inside the type 2 bursts. And with LOFAR especially, we can see these in a lot of detail and even image them. Majority of type 2 bursts are associated with CMEs, and especially CME shocks, but there are a few rare cases where type 2s can occur in the absence of CMEs. So maybe related to mass plasma flows in failed eruptions or something like that. So if you see a type 2, it's very likely that there's a CME ongoing, but it may not be always the case. Okay, so where do they come from? Again, another LOFAR example, nice LOFAR example, type 2 bursts. We have fundamental band here and the harmonic band over here. And if we image them, they usually at this frequency, we would see them on the flank of the CME or on the side of the CME here. So this is the CME in white light images. That's the type 2 radio burst contours. And this is where we would expect to see them. And the reason we see them there is mainly because in most cases, the CME is capable of driving the shock on its flank at these coronal heights. And also at these heights on its flank, it's more likely to meet the conditions to accelerate electrons that produce the type 2 bursts. And if the CME drives a shock, then its speed, so VCME here, has to be higher than the characteristic speed of the low solar corona, which is the Alfvén speed. And the Alfvén speed is simply a ratio of magnetic field of the square root of density. So when the CME speed is greater than the Alfvén speed, it's capable of driving the shock. And in this case, there was some modeling done in this study, and this is the Mach number. So the Mach number is the ratio of the CME speed to the Alfvén speed. And it was found that the CME centroids are in a region where the Mach number is approximately 1.5. So the CME is capable of driving a shock there, but driving a shock is also not enough. It needs to meet certain conditions for the efficient acceleration of electrons. And let's have a look at what happens in more detail. So shocks are quite common in astrophysics, and a lot of people are very interested in shocks. They occur at like discontinuous boundaries. So like supernova remnants, the Earth has a planetary bow shock, or other planetary magnetospheres have a bow shock. And on the sun, what we're interested in are the shocks in front of propagating CMEs. And they're good particle acceleration via a process called Fermi acceleration, which I won't go into much detail. And they can, in the solar corona, they have a low density, so we call them collisionless shocks. Now, what happens is that if you have a CME, the most studies suggest that the CME shock is not uniform. So it's not a smooth surface, but it's curved or it's wavy. So it has to be non-uniform to be able to accelerate particles according to most studies. So we have a curved CME shock. It encounters the overlying magnetic field lines. Now here we can get in the low solar corona, most theories suggest that there's a process called shock drift acceleration that is it's the one responsible for accelerated electrons. While in the higher solar corona, it's possibly a diffusive shock acceleration, for example, that accelerates particles. So there's a bit of a difference between what exactly accelerates electrons. But what happens is that any particles in the vicinity of the shock, they can cross the shock front and gain velocity because of reflections or because of the electric field associated with the shock. And eventually they can escape. And if they escape, then they have higher velocities than the rest of the particles. They create Langmuir waves. Owen's gonna talk about this in a lot more detail. And all that will lead to electromagnetic radiation. So what we need is an inhomogeneous shock and capable of accelerated electron beams. And in the low corona, it's believed that this shock drift acceleration needs to be quasi-perpendicular, like almost very close to a 90-degree angle between shock normal and the magnetic field to be capable of accelerated electrons. And once the electron accelerated, yeah, radio emission produced at the plasma frequency and it's harmonic. And this is pretty much how it's believed that type 2 radio bursts originate. Okay, and just to show you some examples, I showed you this flare before. This is a very nice CME. It was one of the fastest from the previous solar cycle. And you can see here the CME, if I go back, the CME is ejected all of a sudden. And if you look at it in a combination of images, white light and ultraviolet, for example, especially even further out, this bright white stuff is the CME material or the driver. And the fuzzy diffuse thing in white light images here is the CME shock. So this CME was so fast that it was associated with a very, very large shock. And it met this condition, Mach number greater than 1, various locations, especially at the flanks. Okay, and yeah, just to add to this, it's not just electrons that get accelerated by the shock. We can also get protons or some heavier elements. And in interplanetary space, CMEs continue propagating, continue driving the shock. And if you look at this plot here, this is a proton flux. It can continue to accelerate protons for days. So some processes are ongoing at CME shock and proton acceleration even electron acceleration can continue on for a long time. And this is still very well studied because it's very important for space weather. We have charged particles coming our way, then it's bad for the space environment around Earth. Yeah, Agent, have a question?
Yeah, thank you. In the previous slide, how do you identify the shock front? In this case, you don't have the incontinuity in density or particle fluxes, or how to identify the shock front?
There's, I don't know, it's probably a bit subjective, but usually once the CME material stops, then it's this diffuse material here.
Yeah.
That you see outside the CME. So I guess it also depends on how you clip your image. It can probably be a bit subjective, but if you see diffuse material outside the diffuse portions outside the CME material, it's usually a white light shock. I think there's a very famous paper by Vurlidas that initially
okay.
Well, put that in stone, put it that way.
It's everything outside of this noise, basically. It's where you have the smooth gray stuff. That's the front, and then behind it, obviously, is the pile-up compression region and all that shocked material in front of the CME.
Okay.
But yeah, you should read. There are some great papers by Vurlidas et al.
Yeah.
Okay, thank you.
Okay, now we have to leave shocks behind, I'm afraid, because we still have 3 radio bursts to cover. And okay, type 3 radio bursts. So they're almost vertical bursts in dynamic spectra. but they do have a slope, so they're not fully vertical. And they're just electrons accelerated via flare, or I'll show you maybe other processes, and they travel along open magnetic field lines. And because they're plasma emission, again, the electron density decreases, plasma frequency also decreases that way. Higher frequencies are closer to the sun than lower frequencies. And just quickly, you may have seen this yesterday, I'm not sure, but quickly to go through what happens. Here is an example of a flare, sudden energy release and electromagnetic radiation. So what happens there is that accompanying that sudden energy release are also accelerated particles. So we have electrons, especially traveling up and down. The ones traveling down can produce, for example, X-rays, and then hot plasma can fill up the loop, and that's what produces microwave emission at gigahertz in radio. But the electrons traveling upwards are usually the one produces type 3 radio bursts. And in rare occasions, some electrons traveling downwards really high up also can produce some variants of type 3 radio bursts. And this is actually what we actually observe. So even if we don't see the process in other wavelengths, by looking at either radio emission or even X-rays, we can see the accelerated particles. So in this example, we know that there were electrons traveling downwards to produce these X-ray footpoints, and also electrons traveling up to produce, in most cases, it's a type 3 radio burst. And we see with Nancy radioheliograph here, a radio emission right above the flare site. So we see the footpoints and we see the radio bursts. And I guess usually the type 3 radio bursts and the X-ray footpoints are correlated in time. And if we look at other example, for example, if we have a flare there and we do some extrapolations, these type 3 bursts, you see here 3 different frequencies, they do follow the open magnetic field lines. And they don't stop here at relatively high frequencies, they continue on through interplanetary space. So a bunch of type 3 here that continue on to lower frequencies, to kilohertz frequencies. And technically we could track them all the way until they reach us when the frequency of emission decreases and decreases. And this has been done before with the Ulysses spacecraft. So it's quite an old study. They tracked these type 3 radio bursts that originated from a flare, and they could see that they followed the shape, roughly the shape of the interplanetary magnetic field. And the interplanetary magnetic field is in the shape of an Archimedean spiral, and the type 3 radio bursts do indeed propagate that way. So they're a nice way to be able to track electron beams propagating interplanetary space. But currently at the moment, we don't really have any mission capable of doing so. I think the Sunrise mission will be launched in maybe 2023. That's a mini space interferometer that will be able to image even lower frequency type 3 bursts, because at least once they propagate away from the sun, they go below 10 megahertz. So it's below the ionospheric cutoff where we can't see them from ground anymore. So we need to have space missions to see the propagation into interplanetary space. Okay, and I mentioned that flares are usually responsible for type 3s, but 90% of the time or even more, type 3s occur in the absence of flares and CMEs. And this is in a LOFAR example where the sun had some active regions, some small ones, but it was relatively quiet, not even a C-class flare. And multiple type 3 radio bursts occurred. And if you look at LOFAR solar data when there's an active region on the sun, you're most likely, especially in LBA antenna, below 90 megahertz, you're most likely to see a lot of type 3 radio bursts if an active region is present. And you won't be able to correlate them to any large-scale activity that you see in UV or other wavelengths. Okay, this brings me to type 4 radio bursts. Yeah.
Yes, I have a question, please, about type 3 radio burst.
Yeah.
So if we observed an active region from which a solar flare occurred and immediately followed by an eruption of a magnetic cloud, is it possible that some accelerated particles from the solar flare get trapped inside the magnetic cloud itself, and move with it through the interplanetary medium so that it produces that fuzzy emission followed by the type 3 radio burst?
So it is possible for electrons to get trapped inside the magnetic cloud or inside the CME magnetic fields, but I don't think they would produce a type 3 burst. So this brings me to next few lectures where you can see type 4 radio bursts, and rarely they're from inside the CME. But type 3 bursts, they're usually defined that they escape along magnetic field lines, and they're very, very well defined. You can really clearly follow their propagation. But I don't know if you could see something like a type 3 burst inside the magnetic cloud. It's more likely that you see a type 4, as I'll show you in a little bit.
Yeah, I mean, just some particles produce the type 3 radio burst, and some particles are injected inside the magnetic cloud.
Oh, okay, yeah, so
Yes.
that is possible, yeah.
Ah, okay, thank you. Yeah,
sorry. Okay, type 4 burst. Well, I'll mention it briefly how it started and how it's going. In my opinion, they're type of radio burst that is the most loosely classified because the classification dates back from the 50s, and they grouped the continuum broadband emission. So you have this continuum broadband emission here and here. They grouped them all into one category called type 4. And initially, they believe that they can, if you image them, the source can either stay put or move. And initially, they believed that moving type 4s were associated with gyrosynchrotron emission from inside CMEs, so moving outwards with magnetic clouds or CMEs, and stationary type 4s were associated with flares because they weren't moving anywhere. But this is no longer the case. It is possible, but gyrosynchrotron emission from inside CMEs is very, very rare. Only a few studies outlined it. Now, majority of type 4 bursts are associated with CMEs. Like the CME occurs at the same time when we see a type 4 burst. And it's really hard at the moment to find a type 4 burst that is not associated with CME. So it's likely that CME is necessary to see the type 4 burst. And I'll show you this one example quickly just to illustrate the many things type 4s can be. So here we have quite a wide band dynamic spectrum during an X-class solar flare. And at gigahertz, we see a microwave burst, which is continuum emission over wide frequency range, could classify as a type 4. We see another bunch of bursts, continuum emission again over wide frequency range. And at lower frequencies that we're interested in, it's a bit fuzzy because it's from Callisto spectrometer, so nowhere near as good as LOFAR. We see a couple of type 4 radio bursts. And here again, continuum emission, that is not type 4 bursts, which has been studied before, shown not to be type 4 bursts, and a type 2 burst. And if we make an image, let's say at 300 megahertz with an Ansei radio heliograph, so around there, initially we see in this movie, so I'll pause it, these are, it's a different image of post-eruption loops rising. So you can see them rising. There's also a CME ahead of them. Initially we see a massive radio source corresponding to this, and then a more compact moving source. So if you watch that little source there, it moves outwards. And that corresponds to this bit. And this is in just one event. And just with a bit of analysis, which requires both imaging and spectroscopy and an relatively accurate determination of the fluxes of the radio bursts, the first source is actually stationary gyrosynchrotron emission, so the opposite to what it was initially thought. And the second sort is most likely moving plasma emission or a coherent emission mechanism. It's not clear if it's really plasma emission. And it's probably behind the CME where we have a reconnection sheet and it's possible to have continuous acceleration. And here you see the contours of the burst I showed you in the movie before. And later on, when we have the more compact source that's moving that way, the CME is quite far ahead. So the moving source is actually behind the CME and not traveling inside the CME out with it. So
can I ask a question?
Yeah.
You said there that type 4s are usually never seen without the CME.
Yeah.
Now, by that, do you mean also the microwave flare continuum?
Oh, no. So low frequency type 4s. So
Okay.
hundreds of megahertz below. Yes, sorry, I should have specified that. Yeah. I usually don't classify microwaves as type 4s, but I guess they fit into the category. So
yeah, it's the ambiguity in how you label these things.
Yeah, exactly. Yeah. So there's a lot of ambiguity with type 4 bursts, and they require both imaging and spectroscopy to determine what exactly they are. It's a very, very loose category of bursts. But so this case here is just one event. You can also have stationary plasma emission. You can have moving gyrosynchrone emission, or you can have just plasma emission in different positions around the CME. And those are all type 4 bursts, and they could correspond to very, very different processes. And the next slide brings me to gyrosynchrone emission, which again, Owen will explain in a lot of detail next lecture. Sometimes you do see emission from inside the CME, as the question before. So some accelerated electrons can be trapped inside the CME. And this is a very nice example, probably one of the only 2 or 3 very nice examples where the electrons illuminated the internal CME loops. So this is again with an assay radioheliograph. Maybe at some point we will see something like this with LOFAR because it's more capable of getting really good sensitivity. We see gyrosynchrone electrons, so simply electrons spiraling around the internal magnetic loops of the CME and producing radio emission. And using this observation, we can also estimate the internal CME magnetic field at different locations, for example, here, and it was 0.1 to 1.5 Gauss. And this is very important because this internal magnetic field is not known until the CME encounters a spacecraft. So this type of emission was more frequent. It would be very, very valuable to space weather. But unfortunately, I can probably count on my fingers the amount of reports are there. So hopefully we will see more of this with future instrumentation or even LOFAR. Okay, and finally, oh yes, yeah, this was quite an exciting observation. So I talked about radio bursts on the sun, but a lot of radio bursts have been well established on other stars as well. And this is a very recent study that has a clear observation of a burst that fits the type 4 radio burst classification. So you can see a broadband continuum on Proxima Centauri, our nearest neighbor. And it's very, very similar to some type 4 radio bursts on the sun. For example, here we have total intensity and circularly polarized, and it's quite highly circularly polarized, similar to some of the type 4s that we observe on the sun. And it occurs shortly after a flare. This is the flare. So this is a very, very exciting observation from one of our closest neighbors. So it's very likely that we'll observe similar radio bursts on other stars and probably classify them in a similar way they are classified on the sun. But this one here, it's believed to be electron-cyclotron maser emission, which is a coherent mechanism like plasma emission, but it's a different instability, different electron instability. And that's because other stars can have a stronger magnetic field than the sun. And a stronger magnetic field means that the electron-cyclotron maser is dominant over plasma emission. So this is why the author suggested that this is the most likely emission mechanism, while on the sun, it is believed that plasma emission always dominates.
And do you think that it's highly unlikely that this is gyrosynchrotron emission, since the
gyrosynchrotron is very faint.
Yeah.
So I don't know if we'll be able to detect it from a stellar eruption. Like there are other gyrosynchrotron sources, but they're usually like big radio sources in the sky, but probably not a stellar eruption. I doubt it. It's very, very faint. Especially on the sun, the brightness temperature is quite low compared to the other types of radio bursts. There's like almost a 10 to the 3 difference sometimes.
Depends who you ask.
Okay, yeah.
I don't know about the low-far bands, but in the high bands of the VLA, for example, there is some emission from cool stars with high magnetic fields. I mean,
gigahertz.
Gigagauss magnetic fields in the gigahertz.
Okay, yeah. Yeah, so everything I say probably doesn't apply to the gigahertz range. Just disclaimer. Yeah.
Anyway, yeah, it depends on interpretation sometimes. For the moment.
Yeah, we'll see. We have better instrumentation now. Okay, and finally, the last type of radio burst, which is a type 5 burst, which to me seems like it's forgotten. It was either misclassified, or it's simply, I don't really know what's happening with type 5 bursts. I struggled to find really new observations. This is back from the 1980s when they were studied in a lot more detail, but the instrumentation in the 1980s was not great, as you can imagine. Even the type 3 bursts don't show any structure, they're very fuzzy. And this fuzzy continuum that follows a type 3 burst that's called a type 5 could also be a bunch of type 3 bursts that are not resolved. So we don't really know if anyone here hears of anyone studying type 5 bursts, let me know. I'd be curious to see what they look like with modern instrumentation. And sometimes it's separated, so it's a continuum emission following type 3s or group of type 3s, sometimes separated by a few seconds. And one funny thing they found is that the majority of type 5 bursts are circularly polarized in an opposite sense. So type 3 bursts here are left-hand circularly polarized, type 5 bursts are right-hand circularly polarized. And they're most likely harmonic plasma emission. This is based on studies back from the 80s. But now with LOFAR, especially, we can see a lot of type 3 radio bursts happening at the time. And if we image them, we can see those type 3 bursts coming from different locations. So if they are even slightly polarized, because they propagate at different location and they come from different places, it is likely that they could easily propagate in a medium where their polarization would be opposite to other type 3 bursts. So it's a little bit unclear if type 5 radio bursts are their own spectral type, or of course, maybe somebody is studying them, I don't know, but it's unclear if they were just misclassified type 3 bursts. So I don't know of anyone who has a recent example of type 5 radio bursts, but they're still included in the classification. Okay, so that's all I have to say about the 5 main types. And I think I'm short on time. Owen, stop me if I go on for too long. Yeah.
We have 5 minutes to go for the official time.
Okay.
Yeah.
Okay, so I'll quickly go over other types of radio bursts. So the classifications were done in the 50s. So the 5 main types were quickly established, but there's other radio bursts that don't fit immediately into the classification. So one example here is stellar-sww bursts. So here is 5 seconds of data over like 6 megahertz bandwidth with a lot of little bursts. They usually happen with type 3s. They're not necessarily associated with flares or CMEs. So they're just bursts you would observe with LOFAR when there's an active region. Their origin is still unknown. Zebra bursts, this is a gigahertz example, but they also occur at a couple of hundred, few hundred megahertz. And they're just bright bands of emission that look like zebra stripes. And I don't think they have been imaged. So I'm not entirely sure if they have been imaged, but they're probably due to a process called double plasma resonance. So also close to the plasma frequency. And these usually occur inside type 4 radio bursts. So type 4 radio bursts can have multiple fine structures. Another type of radio burst called herringbones, and they're called herringbones because they look like fishbone, something like this. And they're usually associated with type 2 radio bursts. So if you have your type 2, if you had a type 2 emission here, they'll be on either side of the band of emission, but sometimes they occur on their own. And when they occur on their own, they can't really be called type 2, so they have their own name called. And they also associate with CME shock. One example here, I mentioned type 3 radio bursts escape along open field lines, but sometimes they could escape along closed field lines. And we see these J bursts, and J bursts are simply type 3 radio bursts where the emission suddenly stops, most likely because they propagate along the closed loops. And they're just a variant of type 3 bursts. But rarely, very rarely, we can also see something called a U burst, where we're also assuming it's a type 3 that propagates along the closed loop. We can see the emission going up, emission at top of the loop, and emission going back down. but I think U bursts are quite rare. J bursts are more common, and the type 3, of course, are the most common. And I wanted to quickly show herringbones movie, LOFAR movie herringbones. So with LOFAR, it's possible to see all the fine structure. And these herringbones also behave like type 2 bursts. Their emission sources are at CME flank and closely follow it. So with LOFAR, we can zoom in on dynamic spectra, resolve the really fine structure of these radio bursts. So they're quite, this is what, 10 seconds of data. These are quite short, quite narrow band, and image them and see where they originate from. So LOFAR really is capable to look into more and more detail into what happens to radio bursts. Most of the radio bursts I showed you so far, type 1 to 5, and the other radio bursts, they all have fine structure, which indicates that the classic picture, the easy explanations that I showed you so far, they're not complete. There's a lot more going on to it. And I think I'm running out of time. So I guess I'll just leave you with a short summary. And just want to say that radio emission is very important diagnostic because you can see accelerated particles, estimate magnetic fields and plasma density. But it's relatively low cost to observe because it's can be observed from the ground for a very large window, but it's not currently used in any space weather applications as far as I know. And thank you very much. And if you have any questions, feel free. Thank you.
Thank you very much, Diana. That was a really fantastic overview of all types of solar radio bursts, very clear. And thanks everyone for the questions throughout as well. We're slightly over time and into the break, but if there's one quick final question for Diana, I guess we can take one now.
Yeah, can I ask? So do you see a possibility to revisit the classification, like a way to sort of plug all those new types of bursts into a new order of the bursts, or is it too early for that?
I'd love to do that, revisit the classification, but there's a lot of people who still stick with it. But yeah, it's especially type 4s. I think there's some efforts now to try and go over their classification again. And yeah, there's all these other types of radio bursts, but all the other types are not as common as the 5 main types. Then again, type 5 is also not very common, and we don't really see it anymore. So yeah, it's work to be done, I think, and it probably could use a revisit at some point.
Okay, one more quick one. If not, Diana's going to join the Slack channel as well. Yep. Or the workspace, and you can ask her some more questions there, or I guess even by email afterwards as well.
Yeah.
Thank you again, Diana.
Thank you, everyone. Thank you.
So we have a short break now of around 10 to 15 minutes, and we'll meet back here for my talk at 1:15. Okay. Thank you, everyone. Talk to you in a few minutes.
All right. Thanks.